This is Ripple. It's a small temperature box capable of measuring pressure, humidity, and most importantly, ambient air temperature. It's a fun project that I made from scratch, and along the way I learned a lot about embedded hardware and the software behind it. Today, I'm going to share with you my process and hopefully inspire you to make something like this yourself. At the start of summer this year, I began noticing some issues with my AC. It was getting warm inside and the temperature wasn't really keeping up with what I wanted it to be, so I called someone out to come take a look. The repairman showed up pretty quickly and was able to identify the issue as a leaking radiator. Unfortunately, they didn't have this specific radiator in stock, and it was going to take about a week to come in. They also told me that if I used my AC in the meantime, it could potentially damage other things and cause more problems. So I was going to go without AC in the summertime for about a week. Now, I was absolutely miserable. My thermostat was telling me inside was getting to around 30 degrees Celsius, which is around 86 degrees in freedom speak. Only adding to the issue was my my computer, which was also putting out a lot of heat. And unfortunately, where I live, it can get pretty humid. But aha, I thought, I'm a software engineer. I need data. I need to know exactly how miserable I am inside. So I opened up Amazon and started looking for some kind of temperature sensor or probe. But aha, I thought, I'm a software engineer. Why would I just buy something when I can make it myself? And so, for no other reason than that I absolutely can, I designed Ripple. It started off with me digging around in my electronics cabinet. I knew that I had previously purchased some starter electronic kits to tinker with something that I didn't really know a whole lot about, hardware. I quickly found out that one of these kits included a DHT11 temperature sensor. I also knew that I had a Raspberry Pi Pico, and that by connecting these two things, I could probably solve the problem that I wanted to. Now, the first thing I needed to do was figure out how to even use this thing. Luckily, hardware engineers are bound by some of the same rules that software engineers are, and their technical documentation is called a datasheet. Datasheets are really good ways for people who make hardware to tell other people exactly how to use that hardware. As it turns out, the DHT11 is actually pretty old. It's been around since 2009, and it has been improved on several times since then. There's a lot of documentation available for us as well. It did kind of start to fall out of favor because there were a lot of market replacements, and it can be a little inaccurate at times. But it is cheap, and it is fast, and I don't need something that's super accurate, just mostly an ambient air temperature. So I think this will work for what we need. Now, when it comes to hardware and embedded environments, sometimes it can be a little confusing and, quite frankly, overwhelming. Arduino has its own studio, you can program in Python or any of the C variants, you can use pretty much any text editor, so how do you choose? Well, I decided to use Rust for this particular project because I'm not the biggest fan of Python, and C can sometimes be confusing to understand or read. I wanted to pick something that I was familiar with and would be easy for me to explain, but if you decide to use something different, that's up to you. Now, as any good software engineer will tell you, when you're unfamiliar with the territory or you just want to test a couple of things, usually you start out with Hello World. This is a very simple, easy way to test that things are working. But this isn't inside of our computer. We don't have a console attached to it. So how do we get information out of this? Well, by hooking it up to a console, of course. Confused? That's okay. We have a handy little tool called a Debug Probe that we can attach to our Raspberry Pi Pico. This allows us to set breakpoints, get output, most of the things that we would normally do in a debugging environment. Okay, but the actual hello world of the hardware world seems to be something called Blinky. We hook an LED up to whatever we're using and try to turn it on and off. Lucky for us, the Raspberry Pi Pico has a built-in LED on GPIO pin 25. What's GPIO? Well, it stands for General Purpose Input-Output. GPIO pins are actually pretty useful, and we'll see them a lot as we move through this project. They're capable of either sending an electricity value or receiving it. I'm not going to get into the details right now, but I will explain them a little bit later in this video. For now, let's just try to make our LED on pin 25 blink. And hey, would you look at that? There's a blinky. We actually also get some output on our console while it's flashing. Okay, but if you're any kind of software engineer, you've probably already guessed that there's a whole lot more going on than meets the eye with this very simple program. And under the hood, there is a whole lot more, and I'll get into some more details later, but for now, here's a couple of basics. At the heart of the Raspberry Pi Pico, which absolutely lives up to its name, there's an RP2040. This is a very scaled down CPU with some very basic features. In the hardware world, this is generally referred to as a microcontroller or MCU. It understands a very basic instruction set, but there's a problem. It doesn't understand them the same way that our CPU does, and there's not an operating system layer sitting between us and the microcontroller. So we need something else, and that something is called a HAL, or a hardware abstraction layer. Conveniently, Rust already has most of the tools that we're going to need. There's a crate called Embedded HAL that does a bunch of work for us. This allows us to write Rust code for various microprocessors and peripherals, like an RP2040 or a DHT11 temperature sensor. Now, we're actually going to be using a crate called Embassy RS, which is built on top of Embedded HAL, but that has a bunch of features that we're going to need later on down the line. I'll talk a little bit more about my design choices in a later video, but for now, using Embassy RS basically means that we don't need to know any of the details about setting up an RP2040 or driving power to a pin. All we really need to know is that there's a pin that contains an LED, and it's pin 25, and we want to turn it on. Now, you may be asking yourself, aren't we forgetting something? Isn't there a whole other half to this? And the part that we're forgetting is the Debug Probe. But that's actually just another RP2040, and this one's special. It's been set up by Raspberry already and programmed to act as a debug probe, so all we have to do is connect to it. We'll do that by using deformat or deferred formatting and another tool called Probe RS so that we can get output, set breakpoints, and all the other normal debugger magic that we're used to. With some technical details under our belt and with most of the explanation out of the way, let's actually get this Pico to tell us something. But how do we do that? Well, we're going to wire the temperature sensor up to a breadboard and then connect it to the Pico. I'm not going to get into the details of how power works. There are a lot of videos out there made by people who understand this a lot better than I do, and Veritaserum actually has a very interesting video on exactly how power works that I recommend you go check out. Links to that will be in the description. For our purposes, it's basically enough to understand that the Pico receives power over USB and is able to deliver it to other components on the board when we need it. Alright, let's take a look at the datasheet. We can see that we need to hook up a power, a ground, and an I/O pin. There's also a fourth pin here marked NC, but that just means not connected, so we don't have to worry about it. The DHT11 sensor that I have here doesn't actually have that fourth pin, so it looks like someone took care of that problem for us. However, if you want to recreate this project and you do have a sensor with 4 pins, the NC pin is pin 3, which is the pin next to ground, or second from right with the mesh facing up. Now that our sensor is connected, let's actually write some code. Right now we're just looking for a single measurement, but how do we even read this thing? The simple answer is, we have to send some electrical pulses to it, and listen to the electrical pulses it sends back. The more complicated answer, all of this. This looks intimidating, but trust me, we're going to walk through it together. Now, I want to pause for just a moment and briefly talk a little bit more about how GPIO works. Generally, GPIO pins can either listen for electricity or they can send it. And we don't really care about exactly how much voltage there is. We only care if it's close to ground, basically 0 volts, or close to our reference voltage, which is either 3.3 or 5 volts. If it's close to ground, we call that pin pulled low. And if it's close to our reference voltage, we say it's pulled high. GPIO can either set a pin high or low, that is, set a pin to almost no voltage or the reference voltage, or alternatively, it can read whether that pin is close to ground or reference. We can interpret this the same way we do for binary. If the pin is low, that's a 0. If it's high, that's a 1. Now, this is a very simple explanation, but it's really all we need to understand what we want to do. Now, let's try to step through some of this code and understand what's happening. The datasheet tells us that we have to poke the sensor a little bit to get some information out of it, so we're going to do that first. We send the pin low, and we hold it there for about 20 milliseconds. After that, we wait for the sensor to respond for basically as long as we can. According to the datasheet, it should tell us it's ready by setting the pin to high. Now, if you're paying attention, you may notice that we first try to see if the pin is low, but this is more of a sanity check to make sure that the value we originally set the pin to is still the value that it has. Once we verify that's the case, we then wait for the high pulse. Alright, now that our sensor has been sufficiently prodded, it's time to listen for any data it tries to send us. We do that by trying to read up to 4 bytes of data, and we do that by reading each bit individually. The datasheet is telling us that this process is going to have a very specific pattern. The pin is first pulled low, then high, then we receive our bit before the pin is pulled low again, which indicates to us that this pattern is about to repeat. So here in our code, we actually first wait for the pin to go high, and then we pause for 35 microseconds. This is important because it gives the sensor an opportunity to pull the pin low if it wants to send a 0, and we want to avoid any false readings if we can. After the wait, we then read the pin's value, and once we've measured the pin, we can wait for it to go low and return the value. Now, as you can see, there's a lot of timing in here, and it seems to be pretty tight. So how did I come up with these numbers? Well, partially trial and error, but mostly thanks to the datasheet. It actually shows us how long it should take for each bit to be read. The initial prodding to wake up the sensor and take a reading is shown here, and it says that we should wait more than 18 milliseconds, so 20 milliseconds seems pretty reasonable to me. It also shows that a pin should take about 100 microseconds to send a bit in total. But wait, aren't we only waiting for 35 microseconds to read a pulse? Well, inside the conditional read pulse function, we can actually see that we're allowing a wait of up to 1000 microseconds. And we know that according to the datasheet, there will always be a low state, followed by a high state, before the next bit is sent. So, when we're sent a 1, the sensor pin will go high, then go low, then go high again, and finally low to indicate the next bit is about to be sent, which will return our function. When we are sent a 0, the pin will go high, then low, which will also return our function. By waiting up to 1000 microseconds in conditional read pulse, the actual reading time of this function allows us to take about 235 microseconds in total to read a pin and get ready for the next one. Okay, so we can read these electrical pulses, and we can turn them into things we understand, 1s and 0s. We can then assemble those bits into a byte using a mask, and we can get some information out of it. So let's spit this out and see what we get. Now, I should also mention before we actually show the data that the sensor also sends us a checksum to ensure that we have the right amount of data. This is sent in the form of parity bits and is a pretty common way to verify that data is actually read correctly. I'm not going to go into how parity bits work here because Ben Eater has a really great video on this topic, and I highly encourage you to watch his video. A link to that will be in the description. I found almost all of his videos to be very informative and easy to understand, and I really recommend watching all of his content. Alright, let's see what we get here. Well, it's not a temperature. That's because the DHT11 isn't just a temperature sensor, it's also a humidity sensor, which is pretty great because it got pretty hot in my home, but at the same time it felt very humid, so being able to measure both with a single sensor is actually pretty advantageous. But we still need to refer to the datasheet for just a moment, because just sending a number in binary with the current temperature and humidity would be too easy. Actually, it's split into the whole number and the fractional number. So a little bit of simple math should give us exactly what we need. And just like that, we have the temperature and humidity readings for the room we're in. Now, this video is actually getting a lot longer than I had originally intended, and when I sat down to write the script, I didn't realize how much technical detail I would want to go into, so I'm actually going to split this video in parts. Part 2 is going to go into a little bit more about how I tried to display this data, since the Pico doesn't have a screen and we're going to have to attach one if we want to see anything useful while it's not hooked up to a computer. Now, links are going to be in the description for all the resources I use, and I'm also going to put a link to the entire GitHub project. It's going to look a little bit different because technically speaking this project is complete. However, I am designing a PCB, and I'm going to create a video on my process for that and how to assemble it if you want to do so for yourself. If you like this video, or if you want me to give some extra pets to my kitty sleeping back there, please let me know by hitting the subscribe button. And if you'd like to be one of the first people to know when I release part 2, or when the PCB arrives, please consider hitting the notification bell. Actually, as of recording this, the PCB is being shipped to my house, and I'm pretty excited. I'm very grateful for the opportunity to make projects like this, and honestly, your support means a lot. But for now, that's going to do it for this part. So I've been Software Engineer Travis, and I'll see you in the next one.